Okay, so this will be the third video in our 6.6 lesson on solving trig equations. Now, sometimes we have to use trig identities to help us solve an equation. Any of these equations, you could also come up with the approximations of the approximate solutions to the equations, depending on what the interval is, by solving graphically. But if you wanted to come up with the general solution set, or the exact values of the solutions, then you need to use trig identities in order to rewrite the trig equation. Now, this first equation, I'm going to show you one way to solve where I'm going to use two different methods. So the first method is just going to be using identities to come up with the general solution set. The second method is going to be using some extra algebra where you potentially run into extraneous solutions. And I'll leave it up to you. The reason that I'm giving you the two methods, the first method is just using the identities, but it's maybe a little bit more challenging to see. Whereas the second method also works, but I'll just explain why you need to check for extraneous solutions. Okay, so notice that we have sine and cosine in this equation. So we have sine of x minus cosine of x equals to 1. So what I'm going to do is I'm going to use the cofunction identity to rewrite cosine as sine of pi over 2 minus x. So my first line will be sine of x minus sine of pi over 2 minus x equals to 1. And this is not the only way to go about solving this. So if you guys remember when you were verifying identities, there were a lot of different ways to verify the identity. So there are different identities that you could use to rewrite these equations and be able to actually solve them. This is just one way that I saw. So the reason that I have these identities pulled up from 6.4 on the left-hand side, these are, remember, the product to sum identities and the sum to product identities I'm not going to require you to memorize, but I am going to use the second identity here for the sum to product identity. So notice that we have sine minus sine. So the second identity for the sum to product allows me to rewrite the left-hand side of the equation here as 2 times sine of A minus B. So if I'm treating this angle as angle A and this as angle B, so angle A minus angle B would just be 2x minus pi over 2. Okay, and then all over 2 times cosine of angle A plus angle B. So x plus pi over 2 minus x. That will just be pi over 2 divided by 2 equals to 1. Okay, so that was using that sum to product identity. So now I can rewrite the left-hand side. And I just want to, as a disclaimer, I think that the second method is actually a little bit easier to see. It's just you do have to be careful with the extraneous solutions. So this is the only way that I came up with, that using identities so that you don't have to worry about extraneous solutions. But okay, so continuing on, simplifying the argument here, that's x minus pi over 4 times cosine of pi over 4 equals to 1. Well, cosine of pi over 4 is root 2 over 2. So the 2's can actually cancel. And, oops, I can rewrite my equation as sine of x minus pi over 4 equals to 1 over root 2, which if I rationalize the denominator, that gives me sine of x minus pi over 4 equals to root 2 over 2. So then just using the method for coming up with the general solution set, I'll have x minus pi over 4 equals to inverse sine of root 2 over 2 plus 2 pi n, or x equals to pi, oops, I forgot the minus pi over 4. X minus pi over 4 equals to pi minus inverse sine of root 2 over 2 plus 2 pi n, where n is an element of the integers. Okay, we have to add pi to each side. Maybe I'll simplify the inverse sine of root 2 over 2 first. Inverse sine of root 2 over 2 is pi over 4. So pi minus pi over 4 is 3 pi over 4. So now if I add pi over 4 to each side, I'll have pi over 2 plus 2 pi n, or x equals to pi plus 2 pi n, where n is an integer. Okay, so that's method 1, coming up with the general solution set to that equation. Okay, method 2. Let me just copy that. I'm going to paste down here. Okay, so if you didn't see an identity that stuck out to you, so that you could rewrite the equation in terms of the same trig function, like so use all sines or all cosines or all tangents, then you could try some algebraic techniques. So one technique that you could use is squaring both sides of the equation. But if you use that technique, you need to make sure you check for extraneous solutions. So just a reminder, let's say we had a really simple equation like x equals to 2. If we square both sides of this equation, we would get x squared equals to 4. Well, if we look at x squared equals to 4, like think solving that by inspection, aren't there two values that would make that true, a true statement? We would have 2 and negative 2. However, if we look at our original equation, negative 2 is not equal to positive 2. Negative 2 is actually an extraneous solution, a solution that does not make sense. So that's why if you square both sides of the equation, you need to check for any extraneous solutions, okay? So we're going to do that. So when we square both sides, please remember the left-hand side does not turn into sine squared minus cosine squared. You need to think about multiplying out sine minus cosine times sine minus cosine. We get sine squared minus 2 times sine times cosine plus cosine squared equals to 1. You might then see, well, sine squared plus cosine squared, that's equal to 1. That's the Pythagorean identity. So we would have 1 minus 2 times sine times cosine equals to 1. And then if we subtract 1 from both sides of the equation here, the ones cancel, leaving us with -2 times sine times cosine equals to 0. There are different approaches you could use here. Like you could divide by -1 on each side and notice that, well, hey, that's the double angle for identity for sine. So the left-hand side actually ends up being equal to sine of 2x equals to 0. Or from here we could use the zero product property since we have a product equal to 0, where sine of x is equal to 0 or cosine of x is equal to 0. So then the general solution set for each of these equations will have inverse sine, why am I writing a negative? Inverse sine of 0 plus 2 pi n and pi minus inverse sine of 0 plus 2 pi n. And then for cosine, we would have inverse cosine of 0 plus 2 pi n and negative inverse cosine of 0 plus 2 pi n. Don't forget where n is an element of the integers. Okay, simplifying, since 0 is a ratio for sine and cosine on the unit circle. Inverse sine of 0 is 0. Okay, so that would be pi plus 2 pi n. Inverse cosine of 0 is pi over 2. Yes. So pi over 2 plus 2 pi n, negative pi over 2 plus 2 pi n. Okay. Where n is an integer. Here's the thing, you need to double check that each of those solutions, each part of the general solutions actually makes sense. So you could think, okay, if n were equal to 0, so if we were to plug 0 in for x, sine of 0 is equal to 0. Cosine of 0 is equal to 1. Oh, we'd end up with -1 equals to 1. So that actually, 2 pi n is an extraneous solution. If n were equal to 0 for the second piece here, we would have pi. So if we plug in pi, sine of pi is 0. Cosine of pi is -1. So -1 times -1 is 1. We end up with 1 equals to 1. So pi plus 2 pi n checks out. If n is equal to 0 for pi over 2 plus 2 pi n, that would just be pi over 2. So then we go back. Sine of pi over 2 is 1. Cosine of pi over 2 is 0. So 1 equals to 1. That works. If n is equal to 0 in this last piece, that's negative pi over 2. Sine of negative pi over 2 would be -1. And cosine of negative pi over 2 would be 0. -1 does not equal to 1. So negative pi over 2 plus 2 pi n is also an extraneous solution. So our general solution set is x equals to pi plus 2 pi n, as well as pi over 2 plus 2 pi n, where n is an integer. And you can see that that actually matches what we came up with using that first method of just using trig identities. Okay. All right. And this next equation. So what I would do first is get 0 on one side of the equation here. I would also, since the arguments are different, the identity that sticks out to me, remember, there could be different methods, like different steps that you take to solve, different identities that you use. But what sticks out to me is that sine of 2x is equal to 2 times sine of x times cosine of x. And then if I subtract cosine of x from both sides, now I can see that there is a common factor of cosine in that difference. So I can factor out cosine. And now that I have the left-hand side rewritten as a product, I can apply the zero product property. So cosine of x equals to 0, or that would be sine of x is equal to positive 1/2. And then coming up with the general solution set for each of those equations, I would have x equals to inverse cosine of 0 plus 2 pi n. Okay, and then negative inverse cosine of 0 plus 2 pi n. Inverse sine of 1/2 plus 2 pi n. And pi minus inverse sine of 1/2 plus 2 pi n, where n is an integer, an element of the integers. Okay, so simplifying, inverse cosine of 0 is pi over 2. Okay, and so then negative pi over 2 plus 2 pi n. Inverse sine of 1/2 is pi over 6. And then pi minus pi over 6 is 5 pi over 6. Oops. So that's our general solution set to the equation, and we can use that general solution set to come up with the solutions between 0 and 2 pi. So looking at this first piece, if n were equal to 0, we would have pi over 2. If n were equal to 1, that would be plus 2 pi, which would be outside of the interval. If n is equal to 0, negative pi over 2 is outside of the interval, but if n is equal to 1, negative pi over 2 plus 2 pi is 3 pi over 2. Okay, and if n were equal to 2, that would be outside of the interval. If n is equal to 0, we get pi over 6. If n were equal to 1, pi over 6 plus 2 pi is outside of the interval. And then when n is equal to 0, we get 5 pi over 6. And again, if n were equal to 1, we would end up outside of the interval. Okay. So we have sine and cosecant on the left. What sticks out to me is rewriting cosecant in terms of sine. And then now I don't want to have sine of x. We're solving for x. I don't want to have sine of x in the denominator. So what I'm going to do is multiply by sine on both sides of the equation here. So I'll have sine squared plus 1 equals to negative 2 times sine. And then now we have an equation that's like a quadratic. And it factors. It's a perfect square, so it factors sine of x plus 1 squared. So sine of x equals to negative 1. And okay, so if you're using that general method for coming up with the general solution set, you would have the inverse sine of -1 plus 2 pi n, or pi minus inverse sine of -1 plus 2 pi n. And then you see that when you simplify this, well, inverse sine of -1 is -pi/2. And pi minus -pi/2 is actually 3 pi/2. Well, 3 pi/2 and -pi/2, those are coterminal angles. Okay, so we actually can throw one of those equations out for the general solution set. I don't know, let's throw the -pi/2 one out. So we would just have x equals, if you were solving that by inspection, you probably would have just said 3 pi/2 plus 2 pi n, where n is an integer. So what I mean by that is, looking at that equation, you know that 3 pi/2 would be the value, the angle between 0 and 2 pi that would make that a true statement, and all of its coterminal angles could be included by putting the plus 2 pi n, where n is an integer. Okay, so that question was only asking for the general solution set. This last example is asking us for the general solution set, and then the solutions over the interval from 0 to 360. So let's use green. All right, notice that we have sines and cosines. So what sticks out to me is that I could use the Pythagorean identity to rewrite cosine squared as 1 minus sine squared. Okay, so now I have like a quadratic-like trig equation. If we distribute that 3 in, we'll have 3 minus 3 sine squared theta plus sine theta equals to 3. And I could subtract 3 from both sides of the equation, leaving me with -3 sine squared theta plus sine theta equals 0. So in this case, sine theta is a common factor that I can factor out. And the goal of factoring is to be able, and having 0 on the other side of the equation is like when we were solving polynomial equations, is so that you can apply the zero product property, where we know sine theta equals to 0, or this second factor would end up being sine theta equals to 1/3. So theta equals to inverse sine of 0 plus, I'm going to use 360 degrees times n, or 180 degrees minus inverse sine of 0 plus 360 degrees times n. And then for that second equation, we'll have inverse sine of 1/3 plus 360 degrees times n, and 180 degrees minus inverse sine of 1/3 plus 360 degrees times n, where n is an element of the integers. And then we can just clean that up a little bit, since we know what inverse sine of 0 is. Inverse sine of 0 is 0. So that's 180 plus 360 times n. We don't know what inverse sine of 1/3 is. So that is the exact value of that angle and all of its coterminal angles. So that's our general solution set for the equation. And we can use that to come up with our solutions between 0 and 360. So 0 degrees. Okay. And then if n were equal to 1, that would be theta equals 360. That's not on the interval. If n is equal to 0, we would get 180 degrees. And then if n were equal to 1, that's outside the interval. If n is equal to 0, inverse sine of 1/3 is going to be an angle from quadrant 1. Okay, so that will be on the interval from 0 to 360 degrees. That's the exact value of the angle. If n is equal to 1, that would be a coterminal angle outside of the interval. And then 180 degrees minus that angle from quadrant 1 would be on the interval from 0 to 360. It would be an angle from quadrant 2, right? So this would be an angle from quadrant 1. This would be an angle from quadrant 2. Okay. And if n were equal to 1, well, that would be an angle coterminal to that angle in quadrant 2 that would be outside the interval from 0 to 360. So these are all of our solutions. These are the exact values of the solutions. And you could pop the inverse sine of 1/3 into your calculator to get the approximation for that angle. Here, we'll go ahead and do that. And then theta is approximately, make sure you are in degree mode. I get approximately 19.471 degrees. And then 180 minus inverse sine of 1/3, I get 160.529 degrees approximately. Okay, remember when you are solving trig equations or any equation, you are solving for the values that would make a statement true, that would make the left-hand side of the equation equal to the right-hand side if you substituted those values back in. We are sometimes asked to come up with the general solution set to an equation, meaning the solution set that would represent all of the solutions over all real numbers. And then sometimes you are asked to come up with just the solution set over a given interval, and you need to know how to come up with both. My suggestion is going to be to come up with this general solution set first, even if you are only being asked to come up with this solution set over a given interval, and then use that general solution set by picking different values for n, where n is an integer, in order to find those